Hello, my name is John William Lynch, and this is my CSC 480 first assignment. To stay in line with what the PowerPoint slides request for us to show, this is my main driver of my class, and I created a GUI for my code. So if you hit play, it brings up a GUI, and then you can select your options here. So if I want to do best first on easy, I select that, and then I can click run, and then it just outputs everything for me with the output here as well. And then I can put in a time limit here that allows me to check what the differences are there. So that's my GUI. It's very straightforward, and you can mess around with it more if you'd like. My code itself, though, in the full node here, I have a public full node, which is my general constructor, and it takes in an integer of current state. The current state is what you think of a board when you stretch it out with numbers. So the top left of the board would be the index of 0. The bottom right of the board would be the index of 8. So pretty much that's my entire board laid out in an integer array. And the reason I do an integer array is because of my getSuccessor function that's here. This function takes in a parent node, and the parent node grabs into current state, which is this integer array I mentioned earlier, and I iterate through that state, and then I check where the 0th index is. And the reason I want to grab the 0th index is because my successor function then uses that 0th index to determine what location to move at next. So there is a priority of movement here, meaning that if the integer can move up, it will move up before moving to the right, and it will move up and right before moving to the left, and so forth. But pretty much what all of these are saying is that if the if the 0th value doesn't have 0, 1, or 2, so it's not at the top, then we can go into here. But the problem with doing not equal to or here, if I did an or here, that means that it might say that it's not equal to 0, but then my 0th index might be 1, so then I'd be going outside of my board, and then I would get a weird error for that one. And pretty much my logic here is a very basic swapping logic. So it pretty much takes the current value, grabs the one that's above it, which is technically tree states behind it, and then swap them. And then I create a new node with this node as its parent. I increase the depth of the overall node, and then I call it within the numerator as well. To go to my searching algorithms that we're talking about, I was going to show breadth first because that's the most basic one. The breadth first searching algorithm uses a queue and a hash set. And now in all of my algorithms, so I don't repeat it, my hash set is the exact same. I never change it from this one. My explored nodes are going to be strings. And the reason I use strings instead of the integer array of state is because when I first tried using integer array of state, it would give me different addresses of memory. And so actually, even if the integer arrays were identical, they would be in different places. So technically, my hash set would be adding them both there. And that just caused more headache than necessary, so I decided to just change it to string, and my full node has a method to change from integer array to string. These are all extra values here to help with the GUI I showcased at the start, and a lot of my code, I do put a lot of comments, but a majority of this is to help with the printing as well. So if it looks messy, I apologize, but that's the only way that I could get it to work on the GUI. The logic behind my code here is that per algorithm, every time we start this up, we add our very start node to the frontier, and then we also add it to the explored, and then we check if the frontier is empty and we're within the time limit being that little box that I talked about earlier. If we're successful in both of these, then we create a new node from the frontier, we add that into the explored, and then we check if that's equal. If it's not equal, then we do the getSuccessors function, we iterate through all the children of that node, and then we continue on. And the hash set allows us to not have this go on for infinity, as eventually we'll either hit a point where we can't find one, or we do find one, but usually we do find one in all my test cases. It just takes a very long time. Down here is, of course, more stuff for running my GUI. And now the difference between my breadth search and my A1 and my A2 and these more complex searches is it's pretty much identical with everything. The only difference here is my priority queue. So all of these implement the priority queue with a custom comparator. So my A1 search has a comparator that is a normal search heuristic, which is saying get the distance to the nearest goal. And then my A tree search has an A tree search comparator. And my A tree search comparator for extra credit was combining the A1 and A2. So I grabbed the Manhattan distance here, and then I also grabbed the current heuristic distance from A1, and then I combined them with my current path cost, And this value is usually lesser than the A1, but it actually in my test has done better than A2 in some scenarios as well. But it does, all of these show the comparison, and it's just a comparator that overwrites that. Now, I think for my full node, it's the most basic one, so it's a very basic compare, and my full node implements all of these. And these two files up here, one of them is an enumerator and the other one's just a port state. But again, that's my overall project, and if you wanted to test all of these out, this is the GUI. Thank you.